Two apartment buildings stand on the same street. They were shaken by the same earthquake, at the same moment, for the same number of seconds. One is still standing. The other has lost its first floor. The easy answer is that one building was stronger, but that word hides almost everything that matters. The ground beneath the two foundations may not have moved the same way. The buildings may have had different natural rhythms. One may have carried the force through walls, frames, and connections all the way back into the ground. The other may have trapped most of the movement in a single weak floor. So this is not really a story about one good building and one bad building. It is a story about the path taken by a force you cannot see. We are going to send the same earthquake through both buildings, change one hidden variable at a time, and watch the two outcomes separate. And the first variable is not inside either building. It is under them. Imagine a box sitting on a moving table. If the table suddenly slides left, the bottom of the box moves with it. The top tries to stay where it was, not because it is attached to anything above, because mass resists a change in motion. A building does the same thing, only with many stacked floors. The ground moves the foundation. The foundation drags the bottom of the building sideways. Each floor above has mass, and that mass develops inertia as the structure tries to pull it along. Floors begin moving relative to one another. Columns bend, walls distort, connections rotate and stretch. That relative movement is what causes damage. A building can carry enormous vertical weight every single day and still be vulnerable to rapid sideways motion. Gravity presses in one direction, constantly. Earthquake motion reverses again and again. A connection that survives one push may weaken after repeated cycles. A stiff part of the building may attract more force than its neighbors. A flexible part may move farther than it can tolerate. This is why saying an earthquake was magnitude 7 does not tell you what happened inside a particular building. Magnitude describes the source. It does not fully describe the shaking at one foundation, much less the response of every structure above it. Distance from the fault matters. The direction and duration of the rupture matter. The frequencies inside the ground motion matter. Local rock and soil matter. Before the force reaches a single column, the earth beneath the building has already edited the earthquake. Go back to our two buildings. They look close enough to share a parking lot. But one foundation may reach firm material, while the other sits above deeper, softer sediment. That difference can change the amplitude, frequency, and duration of the motion reaching each structure. Think of shaking a bowl of gelatin sitting on a wooden counter. The counter and the gelatin receive the same movement from your hand. They do not respond the same way. Soft sediment can amplify particular frequencies. A deep basin can trap and extend motion. Artificial fill may behave differently from nearby rock. None of this means all soft soil multiplies every earthquake by the same amount. The effect depends on the specific site and the specific motion, but real measurements show how large the difference can become. After the 2001 Nisqually earthquake, researchers studied recordings from dozens of locations around Seattle. At some soft soil sites on artificial fill and young alluvium, motion near 1 Hz was amplified by factors of about 3 to 7 compared with the reference rock site. That number belongs to those sites and that earthquake. It is not a universal multiplier. The lesson is the contrast. Two locations in the same urban area can receive very different shaking because the material beneath them responds differently. The 1989 Loma Prieta earthquake produced an even more visible example. Part of the Cypress Freeway structure in Oakland stood on soft mud and collapsed. Adjacent portions built over firmer ground remained standing. The structure did not cross into a different earthquake. It crossed into different ground. So our first building may already be receiving a more damaging version of the motion before its structural system has any chance to respond. But soft ground has another failure mode. Sometimes it does not merely shake more. For a short time, it can lose much of the strength that was holding the building up. Liquefaction is often described as the ground turning into water. That is memorable, but not quite right. The vulnerable material is usually loose, waterlogged sand or silt. Under normal conditions, grains touch one another and carry load through those contacts. During strong shaking, the grains try to rearrange. Water trapped in the spaces between them becomes pressurized. As that pore water pressure rises, the grain-to-grain contacts carry less effective stress. The soil can temporarily lose strength. Now the foundation may settle unevenly. The ground may spread sideways. A building can tilt even if its upper structure remains largely in one piece. That distinction matters because not every earthquake failure begins with a broken beam. During the 1964 Niigata earthquake in Japan, several four-story apartment buildings tilted dramatically after the soil beneath them liquefied. The image is almost absurd, a building strong enough to remain a recognizable box, yet the ground below it can no longer hold that box level. Liquefaction does not happen everywhere. It requires particular soil and groundwater conditions. It also does not produce the same result every time. But it reveals the first major answer to our question. Two neighboring buildings may not be standing on equally reliable ground. Now let us make the ground beneath both buildings identical. Same soil, same foundation motion, no liquefaction. The outcomes can still separate, because the force has entered the building, and now it needs somewhere to go. Picture every floor as a heavy tray. When the foundation moves, the people, furniture, walls, and concrete on each tray create inertia. Those horizontal forces must be collected and transferred. The floor system carries them toward vertical elements, shear walls, braced frames, or moment-resisting frames. Those elements carry the forces downward. The foundation transfers them into the ground. That is the load path. It is not one object. It is a chain, floor to connection, connection to wall or frame to the level below, level after level, until the force reaches the foundation. If the chain is continuous, many parts of the building can share the work. If one link is missing, offset, weak, or brittle, force and deformation may concentrate around that break. This is why a massive concrete wall on an upper floor is not automatically useful if it stops above an open lobby. The wall may collect lateral force beautifully, then deliver all of it into a level that has no comparable path to the ground. The building can look strong in a photograph because there is so much concrete. Structurally, it may contain a broken sentence. Engineers care about redundancy. If one component is damaged, can another path keep carrying load? They care about how floors are tied to walls and frames. They care about whether vertical resisting elements line up from top to bottom. They care about twisting, because a building whose stiffness is concentrated on one side may rotate as well as translate. None of this means every irregular building is unsafe. It means shape and continuity affect how demand is distributed. For our two buildings, let us give the first one several continuous paths to the foundation. Then let us interrupt the second path at street level. We have just created one of the most recognizable earthquake vulnerabilities, a soft or weak story. At street level, people want windows, shops, garage doors, and open parking. All of those uses can reduce the number of walls or frames resisting sideways motion. The floors above may be divided by many walls and feel relatively stiff. The first floor may be much more flexible or weaker. During shaking, the building does not divide movement evenly just because the floors are the same height. Movement searches for the easiest place to happen. If one story is much softer, a large share of the building's side-to-side drift can concentrate there. Columns at that level bend farther. Connections rotate more. Damage accumulates where the building has the least reserve. The upper floors may remain almost box-shaped, while the first floor leans. That is the frightening part. The weight above has not disappeared. Once the weak level can no longer support and stabilize it, the upper block can descend and trigger a cascading story failure. Earthquakes in the San Francisco Bay Area in 1989 and Southern California in 1994 exposed the vulnerability of many soft story or weak story buildings. But the category needs care. Not every apartment building above parking has the same design. Not every open first floor is automatically a collapse hazard. Real evaluation requires drawings, materials, connections, foundations, site conditions, and engineering analysis. Our simplified experiment only shows the mechanism. Building A spreads drift through a system designed to handle it. Building B concentrates drift into one weak level. Same ground motion, very different internal demand. Now we strengthen the bottom floor of Building B. We add an appropriate lateral resisting system and connect it into the foundation. Problem solved? Not necessarily. A structure can have a complete path and still fail if the links in that path cannot deform without suddenly breaking. People often imagine an earthquake-resistant building as a stone fortress. Make everything thicker, make everything harder, make it refuse to move. But motion cannot simply be voted out of existence. When the ground moves, a perfectly rigid building would have to follow that motion instantly. Its mass would create enormous forces. Real structures deform, and that deformation has to be managed. This is where ductility matters. Ductility is the ability to undergo substantial deformation while retaining useful strength and connection. A ductile component may yield in a planned region and continue carrying load through visible deformation. A brittle component may look fine until a crack or fracture causes a sudden loss of capacity. The difference between those two behaviors can be the difference between a building that absorbs cycles of shaking and one that loses a critical joint without warning. Strength still matters. Stiffness still matters. The point is that neither one is enough by itself. Connections often decide whether behavior is distributed or concentrated. The 1994 Northridge earthquake revealed fracture-prone welds in some steel moment frame buildings. Many failures occurred where horizontal beams joined vertical columns. Those connections were expected to help distribute movement through the frame. Instead, some welds fractured and concentrated damage at critical joints. That case does not mean every older steel building will collapse. It shows why material labels are poor shortcuts. Steel is not automatically safe. Concrete is not automatically unsafe. Wood is not automatically safe. The question is how the entire system was detailed and connected for the demands it may face. Now both of our buildings have continuous paths. Both have stronger lower levels. Both have connections capable of controlled deformation. We shake them again. One still moves far more than the other. The missing variable is time, not the time shown on a clock, the rhythm of the building itself. Push a playground swing at random, and most pushes do little. Push at the right moment, again and again, and the motion grows. Buildings also have natural periods. A short, stiff building tends to move back and forth quickly. A tall, flexible building tends to sway more slowly. Earthquake ground motion contains energy across a range of periods. When a strong part of that motion lines up with a building's natural response, the movement can be amplified. This is why height alone is not a safety ranking. Short buildings tend to respond more strongly to shorter period, higher frequency shaking. Tall buildings tend to respond more strongly to longer period, lower frequency shaking. A distant earthquake can sometimes deliver long period motion that is especially noticeable in high rises, even when people near the ground experience less dramatic shaking. Local soil can also favor particular periods. That creates a three-way interaction between the earthquake, the ground, and the building. Change any one of them and the response may change. Two neighboring buildings with different heights, stiffness, mass distribution, or structural systems can react very differently to the same recorded ground motion. One may be pushed off rhythm. The other may be pushed at exactly the wrong moments. Engineers cannot make a building indifferent to every possible motion. They can estimate hazard, analyze response, avoid dangerous concentrations, and add systems that change how motion enters or how energy is dissipated. That brings us to the part people usually call earthquake proofing. Engineers are more careful with that phrase. There is no single device that turns an ordinary building into an invincible one. Each intervention solves a different part of the force path. Shear walls provide stiffness and strength against lateral movement. Braced frames use diagonal elements to resist racking. Moment frames use rigid beam column connections to carry bending and allow more open space. Proper ties help keep floors connected to the vertical resisting system. Ductile detailing helps critical regions deform without sudden loss of capacity. These parts need to work together. Adding stiffness in the wrong place can create a new concentration. Strengthening upper floors while ignoring a weak bottom story can move demand into the exact level already vulnerable. Installing a strong component without connecting it to a complete path can leave it stranded. Then there is base isolation. Instead of forcing the upper building to follow every rapid movement of the foundation, an isolation layer allows controlled relative motion at the base. Flexible bearings or sliding systems can reduce the amount of some ground motion transmitted into the structure above. The building still moves. The isolators themselves may move substantially. Clear space, utilities, connections, and displacement capacity all have to be designed for that motion. Isolation is not a magic pause button. It is a way of changing the input. Dampers work on another part of the problem. Like shock absorbers in a vehicle, they dissipate some energy and reduce certain structural responses. In one instrumented 55-story building in Osaka, engineers added dampers and buckling restrained braces during a retrofit. USGS compared records from different distant earthquakes before and after the work and found much lower acceleration in the post-retrofit record. This was not the same earthquake replayed under controlled conditions, but it showed how the building's response changed after the retrofit. That is useful evidence, but still not a promise of zero motion or zero damage. The same USGS report notes the building can still experience significant shaking. Every system has limits. Poor soil can complicate foundation behavior, and no device promises zero motion or zero damage. So what does success actually mean? For most ordinary buildings, the answer is more modest than people expect. A code-compliant building is not a fortress that emerges spotless from every earthquake. In current United States practice, the primary objective for typical buildings is life safety. The code aims to reduce the chance of catastrophic failure and large-scale loss of life. Minimizing damage and keeping an ordinary building fully functional after a major earthquake are not always the main explicit objectives. That distinction explains something that often looks like failure. A building may crack, yield, or become too expensive to repair, yet still have performed its most important job if occupants had time and space to survive. This is why no responsible explanation can diagnose a building from a thumbnail. An open storefront is a clue, not a verdict. A visible crack is information, not a complete structural analysis. A modern construction date is not a guarantee, and an old building is not automatically doomed. The useful question is not, does this building look strong? It is, what path will the earthquake force take? Where will deformation concentrate? And what happens when each part reaches its limit? Now we can finally return to our street. Same earthquake, same moment, same number of seconds. But this time, we know what was hidden. First, look below the foundations. One building sits over material that amplifies a damaging part of the motion. The other receives a different input. If loose, saturated soil loses strength, foundation movement may dominate the entire outcome before the frame itself fails. Next, trace the force upward. Every floor produces inertia. Floors collect it. Connections transfer it. Walls and frames carry it down. If that path stops, shifts, or suddenly becomes weak, demand gathers at the break. Now watch the first floor. If it is far softer than the floors above, drift can concentrate there. The building does not need to fail everywhere. It only needs to lose the level carrying everything above it. Then inspect the connections. Can they deform and keep carrying load, or do they fracture suddenly? Is damage allowed to spread through planned ductile regions, or is it trapped at one brittle joint? Finally, listen to the rhythm. Does the earthquake contain strong energy near the building's natural period? Does the soil favor that period? Do isolation or damping systems change the input and remove some energy before damaging deformation grows? This is why two neighboring buildings can reach opposite outcomes. Not because the earthquake chose one, Not because one material is always good and another is always bad, and not because one engineer found a magic device. The earthquake supplies motion. The ground reshapes it. The building turns that motion into force and deformation. The structural system decides whether those demands are distributed, absorbed, redirected, or concentrated into a failure. The difference between standing and collapsing is often a path through soil, foundations, floors, connections, walls, frames, and carefully designed places that are allowed to bend. Earthquake-resistant design does not try to make a building completely motionless. It tries to keep force and deformation from concentrating into sudden failure.